of psychology. I'm going to talk to us about analyzing cultural evolution by iterative learning.
Okay, thank you very much. Thanks for having me here. So a lot of the problems that we talk about in cognitive science are inductive problems. They're problems that require us to reason to underdetermined hypotheses from limited amounts of data. So examples of this are things like learning languages just from the utterances that you get to hear, learning categories from instances of their members where the hypotheses are sort of sets of things and you just get to see some examples of the things which belong in those sets. Or learning, say, a function or a causal relationship by just observing some of the values of a set of variables, right? So you might observe some x, y pairs and try and induce an abstract function that underlies that. So now here's the data and here are the hypotheses. So the way that we normally think about and study these problems in cognitive science is normally in terms of a model, sort of something like this, where we kind of have our learner who is presented with data that's generated by the world, and the learner has to inform some kind of hypothesis about the process that produced those data. But if you think about it for a moment, most of the things that you know probably didn't acquire from this kind of a process. So most of the things that we know don't necessarily come from directly physically interacting with the world and gathering data from the world in that way. Normally they come from data which is provided to us by other people. And if you think about it a little more, those people had the same kind of phenomenon, right? And in turn acquired their hypotheses from data which they were provided with by other people. So this defines a kind of process called iterated learning. So this is a term that was used by Simon Kirby, so I'm just borrowing it here. But basically, where we can imagine a kind of chain of learners, each of whom is generating data which is given to the next learner who forms a hypothesis, who then generates data based on that hypothesis. The next learner forms a hypothesis based on those data, and so on and so on and so on. So given the prevalence of this kind of process in determining the way in which we acquire knowledge, it's interesting to ask a question, what the consequences are of learners learning from other learners in this kind of way. And that's basically what I'm going to talk about today. So the way I'm going to approach this is in two parts. First of all, I'm going to give a formal analysis of iterated learning, and I'll sort of outline some assumptions and then give some conclusions that follow from those assumptions. And then in the second part, I'll talk about some experiments that we've done in the lab that test out the predictions of those models and actually use this as a method for trying to get at some of these questions about what's going on in the heads of individuals in this kind of more standard context that we're used to in cognitive science. So let's start with some formal analyses. So in getting into this, it's worth spending a moment just thinking about the kinds of things that are transmitted by processes like these. So one example is something like language, and this is the example that where I'll actually use mostly throughout this talk, where the languages that we speak, we learn by hearing utterances that are produced by other people who were once themselves, in turn, people who heard utterances produced by other people, and so on. But other kinds of things that obey this sort of process, where really the only evidence that we have for the things that we're learning are provided by other people rather than by the structure of the world, are things like religious concepts or other kinds of cultural conventions, like the fact that, say, at the end of a talk you're supposed to clap. These are things that we kind of acquire by being given examples or observing the behavior of other people and then using that to inform the behavior that we ourselves produce. And in each of these cases, there's an interesting question that people like to ask, either linguists or psychologists or anthropologists, but questions about how it is that the constraints on learning in the heads of individual learners influence the outcome of this kind of process of transmission. So cultural universals, the things that we see across human societies, how those kinds of universals relate to the things that are in the heads of the individual human beings. So as I said, I'm going to use language as the main example for just sort of giving this analysis in the first part of the talk. And this is a good example for the reason that this kind of question about the relationship between universals and constraints on learning is something which has been kind of very well worked out in the theoretical literature on language. So if you kind of take a traditional view of how language learning works, we can think about languages as being the result of basically two factors which are going to determine which language we speak. One is our ability to learn from the world, and the other is some kind of innate constraints on language learning which might come from some process of biological evolution. Taking this view where these are the two factors which determine the structures of the languages that we speak constrains the kind of explanations that you can come up with for observed linguistic phenomena. And in particular, when you look at linguistic universals, the kinds of things that you see across human languages, which range from very sort of core structural properties of languages, like compositionality, where the parts of utterances refer to parts of events in the world, to some, sort of very fine-grained constraints on the structure of human grammars, the way that you're going to end up explaining those universal properties that you see across all of these different languages is going to be in terms of constraints on learning, right? So if you see, when you look across many different languages that are spoken in different communities, that these languages have many kind of structural properties in common, if the only two options that you have are individual learning or some kind of constraints on that learning process as possible explanations for this kind of regularity, well, individual learning can account for variation, but the observation of regularities is something which seems more consistent with some kind of strong constraints on learning. It seems like this is the only source that you could imagine for why you'd see these kinds of regularities. And this is one then traditional argument for something like a universal grammar that places constraints on the languages that we learn. So it's an inference from linguistic universals to some kind of underlying universal grammar. One alternative explanation to this is to introduce another force that could account for the regularities that we see in languages. So, for example, if you think about this process by which languages are transmitted from person to person, then this instantiates a particular kind of process of cultural evolution which has another opportunity to influence the kinds of languages that people speak. So you could imagine that the languages that people speak are the kinds of things that survive that process of transmission, and that process of transmission itself is sufficient to account for the regularities that we observe. So here the idea would be that if we just sort of take a domain general learning algorithm, not something which has any kind of innate language-specific constraints, and sort of look at the consequences of having learners learn from other learners, then out of those processes, we'll end up getting things that have the kinds of structures of human languages. And this is a position that several people have argued for in sort of trying to explain linguistic universals. But whether this position is actually something that works depends on the question that I started out with, what the consequences are of learners learning from other learners. So in order for this to work out, we require a particular relationship between constraints on learning in the heads of individuals and what the outcomes of cultural evolution are going to look like. So if we can answer that question, then we'll know if sort of accounts like this are going to give us an alternative to these inferences about kind of strong innate constraints on language learning. Did that sort of make sense? Yeah? Okay. So what that means is that what we'd like to do is take this kind of process and then give an analysis of what the outcomes of this process will look like as a function of what we put inside the heads of our learners here. And the way that I'm going to do this, the first step is to just sort of begin to turn this into something a little bit more mathematical. So what we'll do is imagine that we have a sequence of learners like this, each of whom observes data, forms a hypothesis, generates data based on the hypothesis, and the next learner forms a hypothesis from those data, and so on. We can turn this into a stochastic process by defining two probability distributions. So one distribution, PL of H given D. So I'm not going to sort of give values to these distributions for the moment. I'm just going to sort of say that these are the distributions that we'll use in characterizing this process. We can just imagine specifying a distribution, which is the distribution over hypotheses, given that you observe particular data. So this is going to characterize our learning algorithm. L here is just standing in for the fact that we're going to have a particular learning algorithm that's going to give us a particular mapping from data to hypotheses. And then a second distribution, PP of D given H. So this is going to be the probability that a learner who has a particular hypothesis will produce particular data, right? And then the process of iterated learning is then just a consequence of iterating these two distributions. So now our next learner chooses a hypothesis by sampling from PL of H given D, and then generates data by sampling from PP of D given H. And this process continues. Where did the hypotheses come from? So in the analysis that I'm going to give, I'm assuming that we have a fixed set of hypotheses and a fixed finite set in this case. So the task of the learner is just to select among those hypotheses. So that's a very abstract analysis, but it's one that characterizes, most learning algorithms are things that you can actually express in those terms. So like linear regression, the hypothesis space is, all linear functions, but then the procedure by which you end up, say, choosing that function doesn't necessarily need to consider all of those functions.
Is culture providing the hypotheses?
No, I'm assuming, so in the analysis that I'm going to give, I'm going to assume that the set of hypotheses is fixed and that the learning algorithm is constant across learners.
So it's a universal.
Yep, that's right. And that's where we're going to get our ability to talk about universals, right? So here, the universal thing is going to be specified by this learning algorithm. And now the question is, how does this learning algorithm influence the outcome of this process of cultural evolution? Yeah. Yep. So these things are going to be constant over time. Yeah. So this defines a stationary stochastic process. And in fact, it gives us, it's something that we can reduce to a homogeneous Markov chain. So basically, I think background that's probably not necessary for this audience, but the basic idea is that what we're going to do is take the stochastic process and then observe that, in fact, what it defines is a Markov chain. So a Markov chain is a sequence of random variables where the probability that a variable takes on a particular value depends only on the value of the previous variable. Having shown that something's a Markov chain is nice because it gives you a way of then characterizing the behavior of this system. So saying that it's a Markov chain, we can characterize its dynamics in terms of a transition matrix that says the probability of going from one value of one variable to the value of the next variable, but also that provided this Markov chain satisfies sort of relatively simply demonstrated conditions, so conditions for ergodicity, it'll converge to a stationary distribution. And what that means is that as time goes on, regardless of the value of the variable with which we start our Markov chain, the probability that the variable towards the end of that chain takes on a particular value converges to a fixed probability distribution. So if we can characterize the stationary distribution of a Markov chain, then that gives us a way of talking about what the consequences of kind of iterating that process will be. So for the case of iterated learning, if we can show that this is a Markov chain and find the stationary distribution, that gives us a way of answering our question about what the consequences of the biases of individual learners will be for the outcomes of cultural evolution, because it tells us what that process will converge to. Okay, so yeah.
Is this a chain of single learners?
Yeah, so I'm going to start out with the case where it's just a chain of individual learners. Yeah, so you can think about it like the game of telephone or Chinese whispers, or where you have kind of just a chain of individuals, each of whom is passing information along. But I can talk about how it generalizes later on. Any other questions? No? Okay. All right. So the way that the process that I defined in terms of talking about iterated learning works is actually something which has this kind of Markov structure. So if you think about it, the hypothesis that, say, the third learner chooses, if you know the hypothesis that the second learner chooses, you don't need to know the hypothesis that the first learner chose, right? So the fact that you're kind of going through this process where you're generating variables, each time conditioned just on the previous variable, means that you have this underlying Markov structure, and you can either analyze a Markov chain defined on hypothesis data pairs for individuals, or you can reduce this down to just a Markov chain on hypotheses, where the transition matrix, the probability of going from a hypothesis for one learner to a hypothesis of the next, marginalizes over the data that the learners see, or a Markov chain on data, where you do the same kind of thing. But having put things in these terms then gives us a set of tools that we can use to work out what the consequences of iterated learning will be. So showing that this is a Markov chain means that for any choice of learning algorithm and production procedure, we can characterize what the stationary distribution will be like. So now the question is, what happens when we make some assumptions about what these learning algorithms are? So in order to be able to talk about how the inductive biases of learners, the things that constrain the hypotheses that they entertain given particular data, influence the outcomes of cultural evolution, we need to have a good formal means of talking about what these constraints look like, a way of talking about what the biases of individual learners are going to be. And the way that I'm going to do that is by talking about learning algorithms that are based on Bayesian inference. So this is the Reverend Thomas Bayes. He gave us the wonderful theorem, which I'm going to use to give us a basis for talking about what the constraints on learning for individual learners might look like. So the basic idea behind Bayes' theorem is that if you're a learner and you are trying to evaluate hypotheses in light of data, then if you are willing to express your degrees of belief in those hypotheses before seeing any data in a probability distribution, the prior distribution, then we can calculate the probabilities you should assign to those hypotheses given the data by just using a simple rule of probability theory. So basically take those prior probabilities, multiply them by the probability of the data given the hypothesis, and then normalize that by summing over the space of all of the hypotheses. So this is kind of a relatively trivial piece of probability theory. The reason why it's interesting from the perspective of being able to talk about constraints on learning is that the prior probability distribution encapsulates the learner's assumptions about the world and about what sorts of hypotheses are easy or hard to learn. So you can kind of think about this. If a hypothesis, so if you have two hypotheses that are equally consistent with the data, in the sense that the probability of the data given those hypotheses is the same, then the prior probability distribution breaks those ties, right? So it expresses the biases that the learners have with respect to those hypotheses. It'll tell you which hypothesis to choose if it seems like they have equal amounts of evidence. Also, if the prior probability of one hypothesis is lower than another hypothesis, then you're going to need more evidence in order to be able to adopt that. And that would normally mean that you'd need to see more data. So this gives us a way of kind of understanding what kinds of things are going to be hard for learners to learn and what kinds of things are going to be easy for learners to learn. If something has a high prior probability, then it's something that they're biased towards and that it's easy for them to learn. They don't have to see a lot of data. With low prior probability, they're biased against and they have to see a lot of data in order to learn. Okay, so just to sort of also get back to this question about what the hypotheses are, it's worth saying in the context of these analyses that what I'm going to talk about is actually an analysis which goes through regardless of what the particular identity of the hypotheses and data are, as long as that basic condition of ergodicity is satisfied. And that's satisfied for relatively sensible hypothesis spaces. So it could be neural networks that represent different languages. It could be some kind of discrete set of parameters where you just have to set the values of those parameters and you know the structure of a language. And when I talk about these prior probability distributions, you shouldn't necessarily think about them as some kind of innate constraints on language learning. Really, what they're doing is just telling us which things are easy to learn and which things are hard to learn. But it doesn't have to be innate. It could reflect other sources of data that you have that might tell you that certain kinds of structures make more sense. And it doesn't have to be specific to language. Basically, there's for many learning algorithms can be expressed in forms which are equivalent to doing Bayesian inference for some hypothesis space and some prior on that space and some likelihood. So in general, we can kind of talk about the inductive biases of learning algorithms in a way that's consistent with talking about prior probabilities. But having expressed, using Bayesian inference as a way of defining our learning algorithms gives us a very broad scope in terms of the kinds of learning algorithms that we consider, and means that we can get very general results about what the consequences of using a particular learning algorithm will be for these kinds of processes of cultural evolution. So the first algorithm I'm going to start out with is going to make the assumption that we just take our learners and we replace them with Bayesian agents. And then we say that our Bayesian agents are going to choose hypotheses by sampling from that posterior distribution. So what we're doing now is saying at each point they see the data, they compute a posterior distribution. The assumption that they're using the same learning algorithm means that they're committed to having the same prior probabilities. And then as a consequence of that, they have a posterior distribution and generate a sample from that distribution, and that sample is the hypothesis that they entertain. So if they're learning a language, they compute a posterior distribution over languages, sample a language from that distribution, and then produce utterances in a way that's consistent with that. And in applying Bayes' rule, they're using the appropriate likelihood. So they're using a probability for the data given the hypothesis, which is consistent with the distribution from which they generate their own utterances. So they kind of have accurate knowledge of the relationship between data and hypotheses. So under these assumptions, we can actually give an analytic characterization of the stationary distribution of that Markov chain. So the Markov chain on hypotheses has as its stationary distribution the prior distribution assumed by the learners. So what that means is that over time, the probability that a learner entertains a particular hypothesis or speaks a particular language converges to the prior probability that's been assigned to that hypothesis or to that language, regardless of the data with which the chain was initialized. So this gives us a very simple kind of result about how it is that inductive biases are going to map onto the outcomes of this kind of process of cultural evolution. And then there's an equivalent result for the data. So the data that they generate will converge to the prior predictive distribution. So that's just the average of this generating function over the hypothesis. So does everyone sort of get the basic result? So convergence to the prior. It means that basically all that cultural evolution does in this context is give people the opportunity for their biases about the hypotheses they're considering to be expressed, right? And the original data washes away. So you can give a sort of simple intuition as to why that would happen. If you think about it, there's one piece of data, right, at the very start of the chain. But every time people make inferences, they're using their priors. So each time that happens, the distribution over hypotheses moves a little bit closer to the prior distribution. And the only distribution that's going to be invariant under that process is the prior distribution itself. And that's the characteristic that defines a stationary distribution. But we can also give a formal analysis of why this happens. And that's a consequence of the fact that the Markov chain that we defined by making this assumption about our learning algorithm is a special kind of Markov chain. It's a Gibbs sampler, which is a Markov chain used in Markov chain Monte Carlo. So the basic idea is behind Gibbs sampling is if you want to generate a set of samples from some joint distribution on a set of variables, the way that you do this is by sampling each variable from its conditional distribution given all of the other variables, and then cycling through this and then doing it again and again and again. And if you iterate that process, it converges to a stationary distribution, which is the joint distribution from which you want to generate. This is also called the heat bath algorithm in statistical physics. And it's a very common Markov chain Monte Carlo algorithm. So again, the way that this would work for, say, two variables, if you wanted to generate from some joint distribution on those two variables, you would start out at some particular point, and the starting point is not going to be relevant in the long run. But you start at a particular point, you then sample a value for one variable, conditioned on the value of the other variable, and then sample a value for the other variable, conditioned on the value of the first variable, and then iterate that process. So you kind of define a Markov chain that's going to walk around that distribution, and asymptotically it'll visit every point with probability proportional to the probability of that point under this probability distribution. So again, to return to iterated learning, if we take our target distribution to be the product of our prior distribution and the likelihood defined by the production probabilities here, then the conditional distributions of this joint distribution are exactly the posterior distribution and the likelihood, the distribution used for generating the utterances. So that's why this Markov chain converges, is that it happens to define the Gibbs sampler for this joint distribution. So it's enforcing consistency between these two distributions that then guarantees that we end up converging to something that matches the prime. Okay, so for this assumption about the way that learners work, we get a very simple statement of the relationship between constraints on individual learning and the outcomes of cultural transmission, right? So when learners are sampling from their posterior distributions, then the distribution over the hypotheses that they entertain converges to the prior distribution on those hypotheses. So this is good news for the traditional story. This plays well on the East Coast, right? If I go and say, well, this means that we have a one-to-one correspondence between the inductive biases of learners and linguistic universals, they say, oh, I knew that all along, right? This says that there should be a direct relationship between those two things. And here, the main novelty is the fact that it indicates that this process of cultural transmission can be the thing that brings out the inductive biases of the learners and allows them to be expressed in the kinds of things that you see in societies. So don't worry if you don't like that conclusion. So this was the first result that we got, and then I talked to Simon Kirby and Mike Dowman, who'd spent a long time arguing for the alternative position, the sort of idea that cultural evolution can magnify the biases of learners. What we did was actually then modify these assumptions and find out that you get very different consequences when you do that. So in getting this result, I made an assumption that learners are sampling from their posterior distributions. But there are many alternatives to this and different ways that you could use your posterior distribution as a Bayesian learner. And one of these is to just say, choose the hypothesis that has highest posterior probability. So we can actually kind of smoothly interpolate between sampling and maximizing by just saying that we're going to generate hypotheses from a distribution that's an exponentiated version of our original posterior distribution. So if we just take this exponent as 1, then we have whatever the posterior distribution was. But as the exponent increases, high probability regions increase in probability, and low probability regions decrease in probability. And so as this exponent approaches infinity, we end up with something which is just going to be a spike focused on the hypothesis which has highest posterior probability. So this is the maximizing case. So for this case, it's harder to give general results. There's actually, again, an analogy with an algorithm that's used in statistical inference. So this is a form of Monte Carlo EM, if people know what the EM algorithm is. And there's been some analysis of that algorithm in statistics. But the way that we analyze this case is actually by looking at certain classes of languages for which the analysis is much simpler. And I can talk about what the property of those languages is that makes it simpler if you're curious. But basically, in this case, what we can show is that the stationary distribution of the Markov chain where we have this exponent r on our posterior distribution is proportional to the prior raised to the same exponent. So what that means is that as you sort of become more deterministic in the way that you're responding in a learner, what you're doing is basically exaggerating the prior in the same way that you're exaggerating the posterior distribution. So hypotheses with high prior probability have higher prior probability, and hypotheses with low prior probability have, lower probability in that stationary distribution. So what we get back is the ordering of these hypotheses that's indicated by the prior, but then the extent to which the distribution favors hypotheses that are higher in that ordering is magnified through the process of transmission. So this gives us the other part of the story. So if we make this small change, and as our learners move towards maximizing, then the influence of the prior is exaggerated. And so what that means is that weak biases can produce strong universals. And that can happen because you can take a learning algorithm that has sort of relatively weak commitments about the difference between two hypotheses, but then have this kind of process of exaggerating the effects in the posterior distribution, which translates into an exaggerated effect in the stationary distribution. So what this means is that actually, yeah, if you make certain assumptions about how learners work, then cultural evolution gives you a viable alternative to these kinds of more traditional analyses of the implications of linguistic universals. It indicates that it's possible for learners with weak biases to produce the kinds of regularities that you might see across languages, and you don't necessarily have the ability to read directly from those universals back to the constraints on learning in the heads of the individual learners. Yeah?
Can you tell us something about how fast
the rate of convergence? Yeah.
The rate of convergence should be the second eigenvalue. It's exponential,
Yeah, it's geometric. Yeah, yeah. So yeah, so all Markov chains are geometric. So you care about the second eigenvalue, yeah, and then for the second eigenvalue depends on essentially the amount of data being transmitted, right? It depends on the fidelity of transmission. So we have general convergence results for some special cases, which I can, for cases like binary parameters, where you essentially have a hypercube. If you get information that determines all but m of those parameters in your data, then you get convergence that's essentially n log n over m, right? Where n is the number of binary parameters, right? And you can use these kinds of analyses of Markov chains to get the same kinds of bounds that you would want for convergence rates. I can talk about specific examples if you want, but there are general results about the second eigenvalues. Yeah. Okay. So one question that came up was that the analysis that I'm doing here is actually just about sort of chains of individual learners. And one interesting question is, the sorts of conclusions we'd like to be able to draw are conclusions that operate at the levels of entire societies. So one thing that's, yeah.
Could you just clarify a little bit more the conclusion here?
Yeah.
When you say explaining the universals, what exactly do you mean?
So what I mean is that if you, so a traditional explanation for universals would be, you see these things in languages, you see these regularities because these are exactly the regularities in the heads of the learner, right? So that would be an explanation for why you would see this consistency across languages. So that you would see that if the explanation for why you see these regularities across languages is because these are exactly the regularities that are in the heads of the learners.
They are what?
Exactly the regularities in the heads of the learners, right? So this is.
Doesn't sound like an explanation to me.
Well, I think it's the way that. So if you want to say make an argument for universal grammar based on linguistic universals, you're essentially making an argument that's along those lines. You say, one piece of evidence for the fact that we have these very strong constraints on language acquisition is that if we look across human languages, we see very little variation in, these fundamental structural properties, right? So that would be that kind of argument. And then, so an alternative could be that the reason you see those regularities is that this process of cultural transmission is sufficient to emphasize, whatever weak regularities there are that are in the heads of the learners.
But it's still, the regularity has to be there.
It has to be there. But I think the fact that it can be weaker means that it no longer has to be something that you think about as being specific to the acquisition of language, right? So it seems kind of hard to come up with reasons why you'd have preferences for, certain kinds of structures over another, unless these were special preferences that you had for sort of, understanding language. If they're very, very, very strong preferences of the kind that a universal grammar would suggest. But if you're willing to say, look, in fact, these biases are weak, and they could just be idiosyncratic because they just sort of happen to be the way that we're built, right? Then it gives you a way in which some kind of more domain general learning mechanism could be sufficient to produce those sorts of regularities across language.
Can you say a few words about the conditions under
Yeah. Yeah. So we've done simulations. Do you mean for the last result? Yeah, we've done simulations where we show that this holds for other classes of languages, but this particular result is obtained by the case where if you consider hypotheses where you have P of D given H, well, if you think about, say, a language as a mapping from meanings to utterances, so your data consists of XY pairs, so you define your likelihood in a way where the probability of seeing a particular XY pair under a hypothetical language is proportional to something which is a function of X or 0. And so the idea is that by doing this, the likelihood cancels when you apply Bayes' rule.
So it doesn't depend on H?
Nope. So whether it's f of X or 0 depends on H. No, well, it's pretty restrictive. Yeah, I'm not claiming it's not restrictive.
But you're trying to make a very general
Yeah, so
conclusion from somewhat restricted.
but we've done more general analyses than this, but this is the case where we can get the analytic result. So the analytic result is, in the case where, so what this does is it means that our likelihood function is something which drops out of Bayes' rule, right? It means that for every hypothesis, the likelihood is constant, and it's either a constant or 0. So all that you're doing then is using the prior to choose between the hypotheses that are equally consistent with the data. So as long as you have hypotheses of the form where the prior is breaking the ties, then you get the result.
Yeah, my only remark is that if H were a grammar and D were a collection of sentences,
Yeah.
then this would never be true.
You mean for like a probabilistic grammar? Yeah.
It would never be true.
No. So the case where it would work is something like, if you think of this as a mapping, and say every hypothesis picks out one Y for every X, right? So if you just think about it as a mapping, and this is indicating the elements of that deterministic mapping. So that's an example which satisfies that condition. And then the events can happen with any probabilities you want, right? It's just that you've defined this deterministic relation between them. Yeah.
This may be a question you can talk to later, but because you said you might talk more about the generalizability of the model.
Yeah.
Either way that you set it up, basically the prior for the learner is sort of the end result that you recognize. So if thinking about applying language evolution for machine, the basic prediction this model would make is that you should always go towards, language should always change to reflect speakers' priors. Is that?
I wouldn't say that, because if you think about how a Markov process works, right? This is a characterization of the stationary distribution. So stochastically, that should be true, right? So if you start off in a situation where, this isn't a very good pen. If you start off in a situation where you're a long way from that prior distribution. So say this is our prior distribution, and you start off over here. Then yeah, you should move towards the state which has higher prior probability. But once you get here, you can wander around as much as you like. It's just that you're going to visit every state with probability which is proportional to that prior distribution. So if you're just sort of wandering around the stationary distribution, then change can look arbitrary. as long as you're within that sort of set of things that has relatively high probability.
I guess I was thinking of this in terms of like binary parameters where, you know, it's kind of like two distributions.
Yeah.
Wandering around makes a little less sense there to me, but maybe that's
Yeah. Okay. Yeah, Jerry?
I guess it would help me kind of bring your overall argument into focus a little more. If you could give a concrete example of the weak bias and the sort of eventual linguistic universal reflection of it.
Right.
The weak domain general bias that gets sharpened into something
Yeah.
which sort of looks specifically linguistic over
Right.
time.
So, I mean, the kinds of examples of this are actually things that come from, Simon Kirby's work. So they've done things like take a neural network learner and teach it some language, and then have that teach another neural network learner, and so on and so on and so on, and show that something like compositionality falls out of that.
Okay.
So this is giving just sort of conditions on how it's possible for things like that to happen. So they believe that always happened, and the first of these results says that doesn't always happen. That there are classes of learners that seem like perfectly sensible learners, for which there's no emphasis of the prior, that you just get this direct correspondence. But that's an example.
Well,
Yeah.
So, I mean, in the Kirby stuff, I think one response that people have had to that is he sort of built that result in, right? He kind of built the preference for a composition language in, and it seems like you're more or less saying,
Yeah.
that's right.
That's right,
And,
yeah.
and he's either sort of building it in
Yeah.
in
So,
a strong version in
right.
your one case, or he's building it in a weak version
Yep.
and you get to amplify.
No, and I'd agree with that. Yeah. So it needs to be there in order for it to come out. Yeah.
So if the learner is using the MAP rule, essentially you're just going to get one language.
No, I mean, so with map it can be, so that's true for, yeah, that's right. So that's true for this case, right? But it's non-ergodic in that case. So you have to be very careful with the true MAP case. Yeah. So it can be for different classes of things. Yeah. Yeah.
Maybe this is way off the mark, and I'm not sure I'm not understanding it at all. But if your example of compositionality being sort of a weak preference, and then does this wandering around once we say, does that make an empirical prediction that you'll find a lot of non-compositional language?
Well, it would predict that. I think it's that that has to be very, very, very highly represented in the stationary distribution, right? But it would predict that it would be possible for you to encounter something that was non-compositional. Yeah.
Well, I mean, the picture on the board looks
Sure.
like you encountered a
But
lot more non-compositional.
But this is the case where I have this as my distribution, right? If I have a distribution that looks like, something like this, where it's all focused on, if this property is, along the axis here is being compositional and being off the axis is non-compositional, then that means that, this wandering around is going to look kind of like this, right? So it depends on how tight that prior distribution is. Yeah.
Yeah, it's still about the same thing. So the compositionality is a kind of very general property.
Right.
Whereas the universals that, like in Chomsky
Yeah.
idea, maybe not.
Sort of Greenberg style. Yeah. Right.
Are much more stricter, very detailed universals, like also about syntactic category.
Right.
So, how is that in the slide? Are you saying that those weak priors are sufficient to have those kinds of strong?
So you could have, if you have hypotheses that have those properties, and you have priors that are weak but favor those properties, right? Then those are things that can be emphasized by a process where people are doing something like maximize. So, but those are the conditions which have to hold. Now it's a separate question of whether that's accurate, right? So now we have a question. This kind of sets you up with a question of, it's about which of these stories is the right story, right? But it's now a story about learners and what's in learners' heads and what learning algorithms people have and so on. It shows that it is at least in principle possible to have a weak learning algorithm that ends up having these kind of strong consequences. And so then the question is, do the kinds of learning algorithms that it seems like people have actually produce the kinds of regularities that we'd want to claim that they can produce, right? So then it's a matter of going out and saying, here's my weak domain general learning algorithm, and in fact it expresses these properties, right? That are the kinds of properties that we see as universals. So it sets up an empirical project of that kind. Yeah. So I'm not making any claims that that's true or not, but it sets up that possibility.
Another strange thing is that there is a unique spatially distribution here. So that means from all initial conditions, all societies will end up with essentially the same distribution.
With the same distribution, yeah. No, but it's so that's right. So there's other. So in terms of thinking about what's missing from this model, this is a neutral model, right? So if you want to talk about how, so first of all, there are two parts of that. One is how come I speak the same language as my neighbor, and that's clearly something that's influenced by the fact that I need to be able to communicate with my neighbor. So there's other aspects of selection that are at work in that case. But the other is how come different communities all speak different languages? Well, that's because they should all be sampled from that distribution. It's not because, you shouldn't have, it'll be the same distribution, but every individual population should be speaking a language which is sampled from that distribution. Yeah?
Is it possible to cut the discussion of the details of the model to saying that, in effect, you are trying to produce proof of possibility rather than making a claim? You're simply saying that you can produce a model where a week prior.
That's all I'm saying. Yeah.
That's it.
And I mean, where I stop is that there are these possibilities.
And we can make the model more plausible or less plausible, or argue whether it's plausible or not. It's just a proof of principle.
Yep, that's right. I'm gonna just go on because we actually have empirical data which bear on some of these things. But it's worth saying briefly that these kinds of models connect directly to the kinds of models of infinite populations in continuous time. So for kind of replicator dynamic style models, one of the things that you need in these models is some information about how it is that a speaker of one language, the probability with which they'll sort of produce offspring which are speakers of another language, right? And you can think about this in terms of, what's the probability that I would acquire a particular hypothesis being exposed to data which are generated by a holder of another hypothesis. Well, in the neutral model, which has fitness taken out, and where we just look at those factors being the things which are influencing the data, the transition matrix that I've been talking about is exactly that mutation matrix in these dynamics. It's the thing that tells you the probability that a Bayesian learner will acquire a hypothesis given that the person who generated the data for them was somebody who entertained another hypothesis. So this gives us the sort of the equilibria of this population dynamics model are equivalent to the stationary distribution of my sort of chains of learners model. But this also gives us a sort of interesting way of trying to study populations by studying chains of individuals, right? If the equilibria are the same, we can actually learn things about the structure of those transition matrices for populations by studying just these sort of chains of learners. And we can use that as a tool for trying to figure out what we should be putting into these models such that we can then draw more general conclusions when we put in things like fitness and so on. Okay. I'm going to go ahead and now talk about some experiments that we've done testing out some of these ideas. So these experiments are interesting for two reasons. One is that they give us a way of just testing out whether the outcomes of cultural evolution, cultural transmission in this way, the kinds of things that we would expect them to be based on this kind of formal analysis. But the other thing is that it gives us a way of getting information about the inductive biases of human learners. So if you think about it, if we care about understanding how people are solving these different kinds of inductive problems, the only way that they can be solving these problems well is by having the correct inductive biases. So the question of how people are doing all of these things is really a question about what the inductive biases of human learners look like. And if these processes of transmission converge to prior distributions or things that are proportional to prior distributions or preserve the ordering, then we can use those processes as a method of gathering clues about the kinds of inductive biases that human learners have. So there's actually a relatively long history of conducting experiments in the lab with human learners that look at these kinds of transmission chains. This is an example from the work of Frederick Bartlett in the 1930s, where he actually started people out. He showed them a drawing. The first person comes into his lab, he shows them a drawing. He then hides the drawing and asks them to reproduce it from memory, and they produce a drawing like this. And then the second person sees this drawing and is asked to reproduce that from memory, and they produce something like this, and then so on and so on and so on, and the owl turns into a cat. So these data are very sort of rich and interesting and have lots of nice things going on. So for example, the point of the most change is the point where the information is the weakest, right? Where the stimulus becomes the smallest and highly ambiguous. But what we try to do is more quantitative analyses of these kinds of phenomena. So starting out by taking cases where we kind of have good ideas about what people's inductive biases look like. Things like function learning and concept learning, where a long experimental literature gives us information about what these biases should be, and then going on to explore what biases look like in other cases where there's more controversy. So to give you a sense for how this works, one of our studies, we basically take the task that I mentioned at the very start, where we give people some XY pairs. They're trying to figure out a relationship between those variables, and we then give them a set of X values and ask them to make predictions for the value of Y. And we take the XY pairs produced by those predictions and give them as data to our next learner. Does that make sense? Okay. So the way that we do this, we put people in a task where X is like the width of this bar. They're trying to guess Y, which is the height of this yellow bar. They do this by adjusting a slider, and they get feedback after they've adjusted the slider as to what the actual height of the yellow bar was. So this is a standard kind of abstract function learning task. And the reason why we use this task is that there's actually a fair amount of literature suggesting that basically people are biased towards learning linear functions. They find them much easier to learn than other kinds of functions, and in particular linear functions with positive slope, and then linear functions with negative slope after that. So what we do is then start iterated learning with different initial data and examine what happens over time. And the prediction is that we should end up converging to a distribution which is common regardless of the initial data. So an example of this, we start out with initial data which come from a positive linear function. The first learner produces predictions that look like this after being exposed to these data. Those data are given to the second learner, who then produces predictions that look like this, which are given to the third learner, producing predictions that look like this, and so on. Okay, and our positive linear function is stable over time. But that's very different from what we see starting with other kinds of initial data. This is a negative linear function. This is a nonlinear function. And this is just random noise. And in each of these cases, we end up getting out a positive linear function at the end. So we've done this 32 times with sets of 9 learners, and 28 of those times we get a positive linear function after 9 iterations. And the other 4 times we get a negative linear function. But it's consistent with the fact that people have a strong bias of this kind. So if you look at the first generation here, you can see a bit of this bias, right? So you can see some of these points have become sort of positive points. Here, this has kind of been learned as kind of a crossover of these two things, but with more emphasis on the positive. And here, these random points have kind of been made a little more positive, looking a bit more linear. But what's striking is that by the time you get over here, it's very clear that people have some kind of underlying positive bias. We've done similar experiments using a concept learning task, where here, each learner would see, say, 3 members of a set of 4 amoeba. And their job is to guess which is the 4th amoeba. And they have 5 options. I'll show you the options in a moment. But the basic idea is that what they're doing is trying to guess who should sort of fill in the rest of the species. And the reason why we do this is because this corresponds to a class of Boolean concepts which have been studied before in the psychological literature. So if you take so basically what we're doing is looking at concepts with 4 members that are defined on 3 binary features. If we take all concepts of that kind, there are 70 of them. But if we ignore the assignment of the feature values to the sort of physical properties in the world, then the sort of symmetries that result from that reduce this down to just 6 types. So the first type is just a one-dimensional set. So this is like all circular nuclei. The second type is a 2-dimensional concept. So this is like big circles or small squares. 3, 4, and 5 are 1 dimension plus an exception. So for example, this is white plus the big black square. And type 6 is the case where no two objects have more than one feature in common. So this is the parity function and requires attending to all 3 dimensions. So the classic result is that types 1 and 2 are easy to learn, and then 3, 4, and 5 are harder, and type 6 is hardest. So our prediction here is that what we should see is a corresponding change in the frequency with which people adopt concepts of this type over time. And the way that we make our iterated learning chains is by showing people 3 examples, having them choose the set which completes that, and then for the next generation, taking the answers that people gave and then sampling 3 at random from those answers and then proceeding in that way. And when we do that, this is what we get. So this is showing the probability of concepts of these 6 different types. This is type 1, type 2, and this is type 6, as a function of number of iterations of learning. And the basic result here is that type 1 increases in popularity over time, type 6 decreases in popularity. And sort of as learning proceeds, we're getting to a situation where types 1 and 2 have high probability and type 6 is going downwards to have a low probability. And that's consistent with, in this case, we can actually make an explicit Bayesian model. We only have 70 hypotheses to consider. We can compute the eigenvalues and so on and show that the dynamics are consistent with that model. And this is using a prior which is estimated from human subjects. So these cases at least give us some kind of previous results from the literature that we can use to calibrate our method to figure out that it really is kind of emphasizing these biases that people have over time. The more interesting cases are situations where there's some controversy about what the, yeah?
Just a question about the type 6.
Why is it so high?
At the beginning.
People like type 6 in our experiment. So the previous results that I talked about that said that type 6 is very hard to learn are based on memory tasks. We use a generalization task where they see everything in front of them, and they just have to choose which thing completes it. In a generalization task, people often choose to complete with type 6 rather than types 3, 4, and 5, because it's kind of got some underlying symmetries, even though, whereas these ones really have a violation of that symmetry. Yeah. Okay. So the case that, one of the cases we've looked at is transmission of frequency distributions. So this is interesting from the perspective of languages, because one of the things that you have to learn in learning a language are the frequencies that are associated with particular kinds of linguistic structures. We use a very simple case, which is a word learning case, where participants will see an object, which will sort of move around on the screen, and then they'll hear a label for that object. And what's varying is the frequencies with which those objects are labeled with 2 different words. So you could see this thing moving around, and it's labeled as dup, 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 or you see it moving around, and it's labeled as neck, neck, neck. And you see these labels with frequencies which vary over time. Which vary for different objects. But the question is how you sort of estimate the probabilities of these labels being associated with these objects and how that affects the way that you produce labels for those objects in the future. So this is controversial insofar as there have been results that suggest that human learners regularize distributions like this. So Carla Hudson-Cam and Alyssa Newport have papers in which they show that definitely children, and in some contexts adults, will take frequency distributions in language and kind of move them towards the more deterministic values. So they'll move values which are closer to 0.5 towards the ends of the frequency spectrum. Whereas Athena Voluminos recently published a paper where she showed, using a task like this, that it seemed like people, adults in this case, probability matched, that they produced labels with probabilities which were proportional to the relative frequency of those labels in the data that they were exposed to. So what we're interested in is actually trying to work out whether people do have a bias towards regularization and using iterated learning as a tool for getting at that. So the basic idea is that you'd see these objects with labels that occur with different frequencies, and then we'd show you the objects later on and ask you to produce labels for them. And the question is, what distributions do you produce when you're given inputs which have different probabilities? So what we actually do is run 6 chains for every learner, where there's 6 different objects, and the frequencies of the labels for those objects vary. So we'd start out showing words which appear with frequencies 0, 1, 2, 3, 4, or 5 out of 10. And then the other word would have the complementary frequency out of 10. Okay, so that's a set of different starting points for our chains. And again, the prediction is that we should converge to some kind of fixed stationary distribution for those different individuals. If we just look at one generation, here are these 6 conditions that I mentioned where we have the frequencies of the training stimuli vary from 1 through 5, and that's plotted with this sort of light gray line. The dark gray line shows the mean frequency of the target label in the responses of the participants for these objects. And what you'll notice is that these things line up pretty well. And this is consistent with some kind of probability matching hypothesis if you just look at these data. And this is basically what Voluminous looked at in terms of analyzing her data. So it looks like there's some kind of, probability matching going on in terms of the way that people are learning these distributions. What's interesting is that if you look at 5 generations, the results look very different. The way that I'm presenting the data here, these are the participants at the top. This is 5 generations, conditions starting in 0, 1, 2, 3, 4, and 5. Each of these chains is one chain of participants. So what you should be able to see is that, say, for 0, most people stay at 0, most chains stay at 0. There are a couple of chains that increase, and then those chains actually increase up to 10. And then you can follow each of the chains of individual subjects across these cases. But the regularity here is that by the end of just 5 generations, all of these chains are concentrated around the ends of the spectrum, right? So producing words with frequencies of 0 or 10, consistent with having regularized this sort of system of frequencies. This is actually showing 2 Bayesian models, one in which we assume that learners are computing a posterior distribution over the value of this probability and then sampling from that distribution. The other which assumes they're computing a posterior distribution and then taking the value with the highest posterior probability. And these models, the intensity shows the probability that they are assigned to a particular state after a certain number of iterations. And both of these models assume a prior, which is a beta distribution, but one that looks like this. So something which is saying that they're favoring the ends of these distributions, consistent with a bias towards regularization. One thing that's interesting is that this map model is actually equivalent to a model which is used in population genetics, so the Wright-Fisher model. So this is a model where you would assume that if you have X copies of a gene in a population of N individuals, the frequency of that gene at the next generation is generated by a binomial draw where the parameter of that binomial distribution is just the relative frequency of the gene in the population. If you allow mutation, where there's some probability with which instances of that gene move towards the other gene, the other possibility, the other allele, and some probability with which they move back, then you get a more general model for which you can characterize stationary distributions and so on. And that more general model is actually equivalent to this iterated learning case where the data that you see are the frequency of a particular outcome and the hypotheses are the probabilities of those outcomes. So in this case, the Wright-Fisher model corresponds to map estimation with a uniform prior. If you have mutation, it corresponds to a particular kind of beta distribution as a prior. And there are connections between these analyses and other models of genetic drift that we're now exploring. The very last case that I wanted to talk about, and I'm just going to do this very briefly, but I can show you lots more data if you're curious. This is something that we've been doing. It's a very large data collection project because we have large numbers of participants in our chains, but we're now looking at transmission of systems of color terms. So what we're doing is basically starting out with some kind of color system and then giving people a couple of examples of the different terms, and then they complete the set of labels for the color chips, and then we produce the examples that are shown to the next person by sampling from the system that they produce. And in doing this, we see some regularities that are the kinds of things that we see across color systems across languages. Okay, so we're sort of interested in trying to use this method to look at inductive biases in other cases. But the basic idea is that this iterated learning method gives us a kind of lens that we can use to magnify these biases. And even though we might be interested in something like how individuals learn, we can actually use this method as a way of making sense of this sort of case of individuals by studying what happens in groups. Thank you. And, yeah.
So one extension of the model you go from the sampling to maximizing.
Yeah.
All the way to H, U, and D.
Right.
I was thinking to a viewpoint of communication, well, I try to communicate some idea to you so that you can sample the right hypothesis. I have to not just manually sample data from my
Right.
hypothesis, I will sample
So that'll decrease the convergence rate, but the same basic result holds as long as I'm using a likelihood function that corresponds to the distribution from which you're generating. So if we do a little bit of game theoretic iteration where you say, well, I know that you're using this likelihood function, so I should generate these data, and then I say, well, I know that you're using your assumptions about my likelihood function to generate the data that you're going to use, and I update my likelihood function appropriately. As long as we're consistent, the same asymptotic result holds. Yeah.
So I think one of the sort of social network effect is the fact that I could be actually learning functions from multiple people giving me data.
Yeah. So I mean, we've thought about it, but we don't have any results. And I think the kind of the part of this that I think is important is when we make these models, that if we make sort of expressive assumptions about the ways that learners work, right, like using things like Bayesian learning, which allow us to be very precise about the inductive biases of our learners, then that can be something which can interact with all of these other kinds of things like, fitness, frequency-dependent fitness, graph-based connections, all of these kinds of things. And, it's interesting to look at how those different factors interact. But, yeah, we don't have any results along those lines. Yeah?
I'm a little confused about the big picture, so I appreciate that this seems a really good way to study biases in the lab, but I'm not sure what you're saying about sort of how it is as a model of learning. You start off by saying that much of what we learn is through this iterated learning process.
Right.
It seems like that you're arguing that just the data gets lost. We just have biases in the end, so to what extent, and how do you account for the fact that cultures do,
Yeah, that's a great question. So I think the basic idea is that this analysis where all that you get from, in terms of the data that you see, is data that's generated by somebody else, applies to a relatively small number of kinds of cultural artifacts. Things like languages, religions, social conventions, things that don't have any kind of basis that's in the sort of physical world. So you can imagine generalizing this to a case where you're now getting data from the world as well as data from the previous person. And now you can say, well, what happens if you get these data as well? Unfortunately, the basic result here is that you converge to the average of the posterior distribution over the distribution that's generating the data. But that's not very satisfying. So we can say, well, what are the conditions on a process of cultural transmission such that you converge to something that's more like the truth? And there's a bunch of answers to that. But basically, it requires that rather than just transmitting data, which doesn't allow you to give any information about your confidence in the hypotheses that you're entertaining, and rather than selecting just a single hypothesis, you be able to communicate something like your posterior distribution over hypotheses, or a set of samples from that distribution. And in those cases, that's sufficient to allow you to converge to something which reflects the truth. So you can get this kind of cumulative cultural evolution going. And we're doing experiments in the lab now where we're looking at this case where we have individuals getting side information and comparing a condition where they just generate data that's seen by the next person with a condition where they type into a little box like their description of basically what they think is going on, and they know the next person will get that. And we do see ratcheting effects in the cases where they're able to sort of communicate that information about what the hypotheses are and how certain they are in them and all of those kinds of things. So yeah, this is kind of the one case where you're not getting those extra pieces of information, and different kinds of cultural artifacts are transmitted differently. Yeah.
We are not given the data. Do you think we will learn the hypothesis according to the prior?
Yeah. So, but if you're asking whether that's a method you could use in the lab for getting at people's priors, the problem with that is that people really don't like telling you things when you've not given them anything to go on. So at least in our experiments, they kind of feel like they're actually solving a real problem, and then as a consequence of that, we can. Yeah.
I'm just very curious. If we are not given the data, that means we just learn the language by our own.
Oh, I see. Yeah.
Is that will be the same with the stationary state when all these languages converge?
Yeah. So I don't know if you're asking about this, but there's a notorious experiment that has historically been done in linguistics where you raise a child in a room with no contact with human beings and see what language they speak as a means of determining what we would perhaps call a prior distribution, but what they thought of as the language that human beings spoke before, they had this kind of Babel incident, right? So there was controversy as to whether, it's been done a couple of times, and there was controversy as to whether it was Hebrew or Phrygian. But, yeah.
Okay. One other question?
Terry?
I'd just be curious to hear a little more about what you found with respect to color categories.
Okay, I can show you. Yeah, I'll just show you results for, so this is for the case where, so what we do is actually, we do this, we want to try and minimize the influence of the fact that everybody speaks English. So we've been trying to give people, instead of just sort of freely evolving systems, controlling the number of color terms that they can use. So this is examples for 2 terms where what we do, these are based on the kind of grids that you were showing. So lightness goes this way and hue goes this way. We initialize chains with either a hue-based, lightness-based, or just a random configuration of assignment of the terms to the colors. And then we look at what happens over time where, each person will see a couple of examples drawn from each of these regions and then be asked to generalize that term to the rest of the array. And then we, sort of take the output of one person as the input for the next person. So for something like 2, you can see pretty clearly here that we get both hue-based solutions emerging spontaneously and lightness-based solutions emerging spontaneously. So here, this is initialized with hue, but we get a transition to lightness here. And here, this is initialized with lightness, we get a transition to hue. But the lightness-based solutions are the things which are more stable over time. So it seems like those are actually favored by, sort of in terms of the solutions that people look at. And, that's consistent with the...
So in those grids, subjects aren't classifying black and white shifts, they're
No.
classifying the
Yeah.
hue correct.
Yeah, that's right. So these are just using that color array that people have. And the colors here are just arbitrary to indicate which terms are being used. So black and white just indicate the 2 terms that could be used.
And those are group aggregate solutions?
No, these are just individuals. So each one of these is one individual who's learned from the previous individual, and the chains go down. And then I'll show you 3 as well is pretty sort of, here we get, this is a hue-based, lightness-based, and random initialization. And here, lightness is persisting for a fairly long time. But over here, for example, you can see hue, then lightness, and we get back to hue, and then lightness again. And over here, you actually see spontaneous emergence of hue-based systems that are very similar to the kinds of hue-based systems that you see in the world color survey. So this is, which one is it? Like, yeah, around here, it sort of looks like Webay or something, right? So, it gets messier after that. So basically, just like the real data, as you add more terms, you end up with messier systems. But you do get sort of relatively coherent and sort of sensible-looking things emerging from these kinds of processes. So this is with just 3 examples of each color per person. We're now doing experiments with more chains which have larger numbers of examples. So they're more stable over time, and we can look at some of the more fine-grained things that are going on. We've done some statistical tests that show that from initialization, the chains tend to get closer to the World Color Survey as measured just by kind of overall distances on the partitions that are induced. But we're now starting to do some more fine-grained statistical analysis.
So trying to minimize the influence of English. How do you do that?
So the only way we do that here is by forcing people to use a particular number of terms. And
Partitioning
yeah, that's right. So we don't have a good way to do this. So if you do the math, the way to solve this problem is to uniformly sample individuals from the languages of the world and put them in your chains. And then that'll converge to a distribution which is actually the appropriate prior. But we don't know how to do that. So.
One interesting experiment is to take individuals from a different culture.
Yeah.
Well, the same culture.
That's right. Yeah, so we've got some planned experiments for other linguistic things along those lines where we can take speakers of 2 different languages that have properties that are rare but high probability across languages, and then see if those high probability properties emerge over time as a consequence of some kind of process like this. So those are examples where we've thought about it. We don't have those kinds of results for colors, but we could obviously try and get them. Yeah.
Yeah, this is a short one. So the regions are not connected?
No, they're not forced to be connected. They're just making these decisions for every chip at a time. So it's remarkable that they end up being as connected as they do, right? So this, the interface is kind of, they can see the chips that they were given as training examples, but they can't see any of the chips that they've assigned.
So this is sort of violating the well formulas?
No, this looks like individual subject data from World Color Survey.
And that's actually consistent with W.R. Garner's structure of information processing, when we talked about polar opposition and symmetry being important for dividing up categorization domains. So there's something actually done already on that kind of result.
Okay. All right, thanks.